Okay, this is our process control project. We designed an in-home water temperature control system.
So the inspiration behind this project was just the fact that many in-home water systems, like a shower or a sink or whatever, have very poor temperature control. They rely entirely on the temperature and pressure of whatever tank or flow stream is behind them. Our idea was to combine multiple streams attached to a controller to basically force the temperature of an outlet stream to a specific set point. We hoped to do this with a rise time of less than 30 seconds and less than 20% overshoot. So as far as our methods, as you can see here, we did this by combining two separate streams of water. So here we have a cold water tank, 22 degrees Celsius, attached to a pump, and a hot water tank, 52 degrees Celsius, attached to a pump. These two streams combined in kind of a Y junction here, and then outlet to the collection tank down here. The idea was that we had our hot water tank pump run at a constant flow rate. We did 200 milliliters per minute consistently, while our cold water tank pump was controlled by a PID controller. It actually ended up being a PI controller. We didn't use the derivative term. And so the idea was by adjusting the cold water flow rate, you could adjust the temperature coming out of the Y junction here. We used the type K thermocouple down underneath to measure the outlet temperature. And so that outlet temperature then being our process variable and the flow rate of the cold water pump being our manipulated variable. Just some of the theory behind this. From a material balance and energy balance, we got this equation here as the kind of the response that should happen in temperature to a change in the cold water flow rate. That gave rise to these parameters when kind of plugging in our constant values and looking at that in Python. And that also gave us then this graph as kind of a simulated ideal response with those parameters. As you can see, we drive to our set point pretty quick. It works reasonably well. We have some overshoot for a larger step change, but on the whole, it was a decent starting point for simulated parameters.
Okay, so to control our actual hardware that we built, we used LabVIEW because it has this built-in advanced PID function. So over here we have the front panel, which is just how we interacted with and controlled the system while it was running. And over here is the block diagram. So we have the wiring, and basically we just have 3 DACs. This is an input DAC where we just measure the temperature from that type K thermocouple. And over here these two are for controlling the pump. This is an analog output DAC where we took the output from the PID controller and used it to control the cold water flow rate. And this one is just a digital output, and it's just the pump on-off switch. So then lastly, we just have all of those signals writing to this Excel file. So we have the temperature of the system, the temperature set point, and the pump flow rate. So this was our apparatus. We have 2 pumps and 2 reservoirs. Over here is the cold pump, so this is the one that we were actually controlling, and this was the hot one, so we kept this at a constant flow rate of 200 milliliters per minute. Over here is the thermocouple wiring, and this is the wiring that we used for the pump. And then we just have a video of our system responding to a set point change. So you'll see that this flow rate is going to go up to adjust. And this flow rate, this is the hot pump, it's just going to stay at that constant 200 milliliters per minute. So these are the results of our experiments. This first graph is using those first PID parameters that we discussed earlier. The blue dotted line is the simulation data, so we've already seen that. And then the red line is the experimental data. So we can see that our model did match the data pretty well, and the controller did work. It was driving to a set point. It was just very sluggish. And over here, it didn't ever actually reach the set point, so we decided to tune it to be more aggressive. So we ended up with these PID parameters that produce this graph. As you can see, it reaches the set point pretty quickly, and there's very little overshoot, so we thought this was a pretty good PID controller.
So just some recommendations then, if this were to ever be turned into an actual product or more research were to be done going forward. Obviously, you would have a range of acceptable parameters depending on what your priorities were. You could change your gain, you could change your tau I. These graphs correspond to different tuning. The green line is the most aggressive tuning. You can see it goes to the set points the quickest. Red is more conservative, but obviously if you were in a system where you were worried about overshoot or oscillation, you might want to have more conservative tuning. One last thing that we found interesting, this is the data from our very last run. This system was not first order simply because the overall flow rate was not constant. Since we were keeping our hot flow rate constant and varying the cold flow rate, That meant that when we were shooting for higher temperatures, the overall flow rate was lower. This gave rise to this interesting phenomenon where for a given set of parameters, high temperatures would seem underdamped. You can see here we have large overshoot and oscillation, whereas low temperatures would be just fine. I mean, this looks like an excellent convergence to the set point without any overshoot whatsoever. So if more research were done, it would be worth looking into either gain scheduling or maybe fitting the system to a higher order, or some other way of accounting for this fact that the parameters do seem to affect the system differently at different temperatures.
All right, that is our project. Thank you for listening.